What if I told you we could understand language in a completely new way? I mean, not just by reading words on a page, but by actually seeing them, by visualizing the hidden geometry of meaning itself. That's exactly what we're going to dive into.
Okay, so let's start with something we all know, a regular map. When you look at one, you can basically measure two things. First, there's the simple straight line distance. How far is it from point A to point B as the crow flies? And second, you can look at the trajectory, the actual path you take with all its twists and turns. Pretty straightforward, right?
But here's the big leap. What if we took that same idea and applied it to language? What if every single word, every sentence we write exists as a point on this huge invisible map of meaning? Well, all of a sudden, those two simple ideas, distance and trajectory, become these incredibly powerful tools for understanding how an AI actually thinks. Let's dig into that first idea, distance. We're going to use it to tackle a problem that, let's be honest, anyone who's ever used an AI has run into. Just getting the darn thing to follow your instructions consistently. Welcome to the geometry of compliance. Now, this map of meaning has a technical name. It's called an embedding space. You can just think of it as this massive, multidimensional space where every piece of text gets plotted as a coordinate. And the most important rule here is super simple. Text that means similar things are close together on the map. They're neighbors. So, this brings us to a really common frustration. You give an AI a clear command, it might even say, sure, I can do that, but then nothing. It just doesn't do it. Why does that happen? Well, the answer might actually be geometric. And the technique for figuring this out is called prompt geometry. The thinking is that AI models are trained to be, well, helpfully evasive when you give them certain direct commands. Prompt geometry lets us measure the semantic distance between different ways of saying the exact same thing, so we can find a phrasing that the AI is just less likely to ignore. So take a simple command like file bugs. To a human, all of these variations on the screen pretty much mean the same thing. But to an AI, each one is a totally different point on that map of meaning. The direct command, file bugs, that's our baseline. But what about saying it in the passive voice, like bugs are filed, or using a presupposition, like after filing? Do they land in a different neighborhood on the map? And here's where it gets real. We can actually measure this stuff using something called cosine distance, which is really just a way of measuring the angle between concepts on our map. We see a huge difference. Just look at how far that presuppositional phrasing drifts away from our baseline command. The main takeaway is that this isn't just a feeling we have. It's a quantifiable geometric fact. Okay, but does this distance on the map actually change how the AI behaves in the real world? Well, to find out, some researchers designed this beautifully simple and, kind of quirky experiment called the Spedunkel test. The instruction they used is perfect because it is completely unambiguous. The AI either starts its response with the word Spadiwinkel or it doesn't. And since it's a totally made-up word, the model would never say it by accident. It's basically the perfect canary in the coal mine for checking if an AI is actually complying. And just for a bit of fun trivia, the word itself has a pretty great backstory. It was just a placeholder word in a Trey Parker musical that ended up being too funny to replace. A fittingly absurd name for a test of AI obedience, don't you think? This whole thing brings us to a piece of, let's call it folk wisdom, that I'm pretty sure we've all tried. If the AI isn't listening, maybe we just need to be more emphatic. Does typing in all caps or adding a bunch of exclamation points actually do anything? Well, instead of just guessing, we can actually form testable hypotheses. Does yelling have no effect? Could it actually be counterproductive? Or is there maybe a tiny benefit? With geometry, we can test this. If yelling doesn't significantly move the command's location on our map, then it's probably just a waste of keystrokes. So, we've seen how the static distance between 2 points on the map can predict an AI's behavior. But what about the other part of our map analogy, the journey itself? What if we analyze the trajectory? This means we have to start thinking about text not as a fixed point, but as a particle that's actually moving through this map of meaning. And that's the whole idea behind semantic trajectory. By tracking a string of sentences as a path through that embedding space, we can suddenly start applying the laws of physics. We can calculate its velocity, how fast the topic is changing, and even its acceleration, which helps us understand the rhythm and structure of the writing itself. Let's break that down real quick. So every sentence has a position on the map.
The distance to the next sentence gives us its velocity, or what you could call its pacing. And then the change in that pacing, that gives us its acceleration. And this last part, acceleration, is where we find all the hidden fingerprints of an author's style. And this leads to a really profound insight. It's not just about what a text is saying. Often, the most revealing signal is the rhythm of its journey through meaning. The pattern of its acceleration holds this unique signature, almost like a fingerprint of style. And this brings us to a genuinely wild application of this whole idea. By analyzing these trajectories, we can actually detect the geometric fingerprint of literary absurdism. The research found two really distinct styles. First, you've got the Douglas Adams style, which they call the deadpan snap. Everything is calm, calm, calm. Then there's this sudden massive spike in acceleration, and then right back to calm. Then there's the Joseph Heller style, the bureaucratic trap. Here, the text just moves in circles, slowing down and down as it gets caught in its own looping logic. And this is a brilliant illustration of how we can actually measure it. The Adams fingerprint isn't just one thing. It's a combo of signals. You need a few very isolated spikes that really stand out from an otherwise stable background pace. It's the contrast that makes the whole thing work. The Heller fingerprint is completely different. For this one, we're looking for circularity. The text keeps coming back to the same areas on the map. We look for lots of similar sentences that don't actually move the story forward. And crucially, we're looking for deceleration, as the whole thing just grinds to a halt in a loop of its own logic. And here is the payoff. When we run different kinds of text through this analysis, the theory holds up perfectly. Adams scores high on the deadpan metric, and Heller scores high on his. But check out the generic wacky text. It has the spikes, but it doesn't have the underlying structure. And this is the amazing part. This tool can actually tell the difference between deliberate literary craft and just random weirdness. So to wrap this all up, we've basically looked at two powerful new ways of seeing language. Prompt geometry measures the static distance between commands to predict how an AI will behave, and semantic trajectory measures the dynamic shape of a text's journey to reveal the hidden fingerprints of an author's style. It really makes you wonder, doesn't it? If we can find the mathematical signature for something as subtle and human as absurdist comedy, what else is hiding in the geometry of language? What other patterns of rhetoric, or persuasion, or poetry are just sitting there, waiting for us to find the right lens to finally see them?